Hello everyone and welcome back to another mathematics tutorial. Today I'm going to be talking about topological spaces. Okay, this is an introductory video, so I'm going to go over the definition of a topological space, give you some examples, and just things to look out for when you're dealing with topological spaces. Now, we've got to start off with the definition, obviously, otherwise we won't get anywhere. And the definition is, it may seem a little bit long at first, so it's important to read it through slowly and try and sort of carefully understand it. But the thing I want you to bear in mind is that a topological space is really a generalization of a metric space. So I have talked about metric spaces before. If you haven't seen my videos on that, do check them out. I'll put some links up. But a topological space really is generalizing metric spaces. So in a metric space we had a notion of distance. We had some kind of a distance defined on our metric space. In a topological space we don't really have this notion of distance. We just have some other conditions, and it's kind of a looser structure than a metric space. But enough of that, let's get into the actual definition. So I've got a little bit of text on the screen. I've said let X be a set, so X is some set, capital X, and a topology on X is a collection, capital T, of subsets of X with the following conditions. And I'm going to write these conditions down in just a moment, but the thing I want you to pay attention to right now is the topology is going to be a collection of subsets of X. So it's going to be a bunch of subsets of X, okay? With the conditions that I'm about to write down, okay? So number one, I'm going to insist that X and the empty set, remember this symbol denotes the empty set, I'm going to insist that they belong to the collection T of subsets. So I'm taking a bunch of subsets of X, and one of my conditions is that I insist that X and the empty set have to be included in that collection of subsets. Okay, so I have to take X and the empty set in my collection. Okay, I can take other sets as well, but I definitely have to have these two. Okay. Number two is a little bit more complicated, but it's not too bad. So the union of sets from T is in T. Okay, so this may seem a bit strange at first, but essentially what I'm saying is if you take any number of sets in T and you take the union, then the result should also be in T. Okay, so it's any kind of union you like. As long as all of the individual sets are in T, if I take the union, then that answer should also be in T. So we can write this down slightly more mathematically if you can't visualize this. So essentially what this means is, i.e., given, let's say, ui in T, so this is a u subscript I, for I belonging to some index set capital I. So this is an index set, so I could be natural numbers, it could be a finite set, so it could be maybe just three sets, so it could be u1, u2, u3, or it could be infinite, it could be u1, u2, u3, u4, and continues on forever. Or it could even be uncountable, okay? It could be, you might have a set ui for every real number I, and that would be an uncountable collection of sets, okay? So just be careful there, it might not be a finite number of sets, or even a countable number, it could be a very nasty number of sets. But yeah, so given this, then the union over I in the index set I of the UIs. So let me just make my union symbol a little bit bigger there so you can distinguish the U and the union. So the union over the UIs is in T. Okay, so I take a bunch of sets in T, I take the union, and the answer should be in T, okay, regardless of how many sets I took. Okay, hopefully that's clear. We are going to go over some examples because this is quite abstract, and it may take you a little while to get used to it. And then finally, if I can just squeeze in the last condition down here, I haven't given myself much space. Number 3 is going to be similar to this union, but with intersections. Okay, but the key thing here is I want it to be a finite number of intersections of sets. Okay, so here the union, it could be any number of sets, but with an intersection I'm going to want it to be a finite number. So given let's say let's call them something different, shall we? Let's call them B1 up to Bn in T, then the intersection over I equal 1 to n of the Bi's should be in T. Okay, and this should work for any natural number n. Okay, so this is for any arbitrary natural number n. If I take any finite number of sets that are in T, then the intersection should also belong to T. Okay? You don't know about an infinite number. Okay, so if I took an infinite number of sets here, the intersection might not be in T. Okay, I'm only requiring the finite number of intersections. Okay, so the key thing to remember is this first one. It contains X itself and the empty set. It should be closed under any kind of union. So if you take any number of sets in T and take the union, it should also be in T. And then the third one is the same as the union, but it's a finite number of sets with an intersection. Okay, so this is quite an abstract definition, so don't worry if you don't understand it just yet. We're going to go over some examples so that you can see, you know, how to apply this and to help you remember it as well. So let's do just that. I will erase the definition, so I'd suggest if you haven't written it down, just pause the video and write it down. Maybe add your own notes to it, so maybe add the fact that this needs to be a finite number of sets here for the intersection, and it can work for any number n provided that it's finite, and then maybe you want to add that the union can be an arbitrary number of sets. Okay, but the important thing is to remember that these conditions all hold. So just write them down, and that'll be your definition of a topology. Okay. So I'll erase this, and we will get started with some examples. Math is actually quite fun when you think about it, isn't it? Sometimes, at least. Some of these definitions can be a bit dull, but hopefully this one isn't too bad. So let's start with a simple example. Okay, I'm going to let X be a set. X is any old set, and actually I'll insist that X is not empty. Okay, I just to make it a bit more interesting, it's not empty. Okay, then take T to be the collection X and the empty set. Okay, so remember, when I'm talking about a topology, I want to be taking a collection of subsets of X. Okay, so X itself is a subset of X, and the empty set is a subset of X as well. The empty set is a subset of every set, so that's fine. Now, what do we have to check? We have to check some conditions, don't we? Do we remember what those conditions are? And those conditions, I will write them down now, but the conditions are the first one, X belongs to T. Yes, it does, because I included it in there. And phi belongs to T. Phi, the empty set, yes. So the empty set belongs to T. So X is in T and the empty set is in T. So good, the first condition is met. Okay, so you do have to check this. Sometimes it's obvious, like here. I have explicitly included them, but sometimes it's a bit tricky to see. So you just have to check and make sure. So that's the first condition. Number 2. Now, I said that if I took any number of sets in T, the union should be in T. Okay? Now here, I only have 2 sets to choose from. Okay? So, if I take some sets from here, they can only be X or the empty set, or a mixture of both. Okay? And if I put the empty set in there, it's not going to affect anything. And if I put X in there, it's also not really going to do anything either. So let me just illustrate that. We know that X union X is going to be equal to X. And X union the empty set is going to be equal to X. And the empty set union the empty set is going to be the empty set, indeed. If you union 2 nothings together, you get nothing. But yes, so you can see that regardless of what's in the union, the answer is just going to be X or the empty set. And remember, I did say it had to be closed under any number of unions, right? So I could have any number of sets. But even if I take an infinite number, they can still only be X or the empty set. So I'm still going to end up in one of these cases. Okay? So this doesn't really cause any problems at all. So we've checked union is going to be either X or the empty set, which are elements in T. Okay, so that's good. That condition is also met. What about the other one, the finite intersection property? So if I take a finite number of sets from T and I intersect them, the answer of the intersection should also be a set in T. And this is also true because, again, I've only got 2 sets to choose from, so I just need to check X intersected with itself is just X. X intersected with the empty set is the empty set. And the empty set intersected with the empty set is the empty set, which are obviously still sets in T. Okay, and this applies to any finite number of sets that I take from T, because I only have these 2 options. So, in that, if I take, let's say, B1 up to, just to kind of illustrate this a bit, if I take B1 up to Bn in T, then they can only be X or the empty set, each one, right? So somewhere in the intersection from I equal 1 to n of the bi's, I will, somewhere in this intersection I'm going to end up with some x's and some empty sets, and we've seen all the possible combinations here, so the only thing I can end up with is x or the empty set, which is certainly in T. So that's good. All 3 conditions checked. So that means that T is a topology on X. Okay, these are the conditions that you need. You need it to be a collection of subsets satisfying those 3 conditions. Okay, hopefully that illustrates things. we're going to go over a slightly more, well, I say slightly more complicated, it's not that complicated actually. There's just more sets to consider. So that one was quite straightforward, the one we just looked at, because there were only 2 sets, okay? Another one, let X be a set, and again, X is not empty. You can have X being empty, but I'm just making it non-empty just so it's a bit more interesting. So X is not empty. Then we're going to take T to be the power set of X. Okay, and remember, the power set is the set of all subsets of X. So it's every possible subset, including the empty set. Okay, every possible subset. Is it a topology on X? Yes, yes it is. After all, I wouldn't be showing you something that wasn't a topology. Though maybe I will do that later. I'll show you some things that aren't topologies. Okay, but yes, so the power set is a topology. Why? Well, we need to check these conditions. This may seem kind of boring if you've grasped it already, but it's quite instructive to go through each condition and check it yourself just to make sure you really understand what's going on here. So, condition number 1, I need X and the empty set to be in T. Well, X is a subset of itself, so it's in the power set. So X, I can write X is a subset of X, so X is in T, and the empty set is a subset of X, so the empty set is in T. Nice. Condition number 1 checked. Condition number 2. Well, if I take some subsets of X and I union them together, I still have a subset of X. I'm essentially saying, given UI for I in an index set, capital I, and let me put UI is in T. The UI is in T always. We have the union. Let me just put over I in I, capital I, of the U little i's, is a subset of X, so is in T. And if you want to sort of check this more thoroughly, you know that each U, individual U, subscript little I, is a subset of X. So the union is also going to be a subset of X, because if you take something in the union, it's going to be an element of X, because it belongs to one of those little U subscript i's, and therefore, since they're subsets of X, it's going to be in X, so this will be a subset of X. So this is in T, so we're good. And it's the same thing for the intersection, really. You can't really, I mean, it's quite simple to see. It's just the same argument, really, with the union. If you take some subsets of X and you take the intersection, then you have a subset of X again. So 3, let me just put similar to 2. Hopefully you can see that. Maybe try and write that one down yourself just so you can practice using the definition. Okay, so I've given you a couple of examples. What else should we go over? Well, it's important to remember there are quite a lot of topological spaces, okay? So a set, X, can have many different topologies. Okay, so we saw, let X be a set, X not empty again. We saw, let's say T1 equal to X and the empty set, and T2 equal to the power set of x are topologies on x. Okay, so we saw that. So there can be many different topologies, so you have to be careful which one you're talking about. Okay, if you're considering a few different ones, you want to be clear which one you're focusing on at that particular moment. Okay, now one more thing, and this is where I'll leave it for now, because I will be doing some future videos on this. Don't worry, there will be some more advanced topics coming. But for now, we refer to sets in a topology as open sets. So i.e., if you take that collection T, the topology, a set in T is called an open set. Okay, it's called open, and that's just what you mean. If you say an open set, you mean a set in a topology. So i.e., open set U means U is in T, where T is a topology on X. Okay, and this means that U is a subset of X as well. So also U is a subset of X. Okay, so you might see a lot of different notations here, or lots of different words. So if you see open set, it means it's in the topology, and it will mean it's a subset of the space X as well. So if you know you have a topology on X, and you say you see an open set U, that means it's in T, and it's therefore a subset of X. Okay, so this is just kind of notation here. Just mathematicians like to come up with a lot of notation. It's just open set means a set in the topology. Okay, so if I illustrate this just very briefly before finishing, e.g. X not empty, T equal X and the empty set, saying U is open in X or T. Sometimes you might see that, so they'll say it's open in X or it's open in T. Sometimes they just say U is open, but that means U belongs to T, which in this case is equal to this particular collection. So here U is X or U is the empty set, because there are only two to think about. But obviously if the topology is bigger, if there are more sets, then you don't know what U is going to be equal to necessarily. But that's just what it means. To say U is open, or an open set, in X or in the topology capital T, it will just mean that U is one of those subsets that's in T. Okay? I hope that clears things up for you. In a later video, I'm going to do some more examples, so I'm going to go over more topological spaces, and I'll also go over things that aren't topological spaces. Maybe I'll give you some counterexamples so you can see where the definition goes wrong. And then I'll go over some more advanced topics as well. So thank you for watching. Do try and leave feedback if you can, or if you've got questions or anything, just leave a comment. I do appreciate constructive feedback, and I'll try and listen to your requests. Don't forget to subscribe, and I'll see you next time.